the video started?
Now the video is started.
Okay. Alright, so first I can go over like the basics of digital logic because I think it's pretty cool. Oh yeah, so the goals for this project, I wanted it to be relatively simple, so only basic logic chips used, not anything fancy. So like I can't plug like a NVIDIA GPU into it or anything. And I did like want it to be able to run Tetris or at least something like complicated, not just like add numbers and nothing else. Alright, so like the most basic piece of information is a bit, which is in either one or two states. And bits are used to, I'll talk about that later. So in the computer, bits are voltage levels. So the power supply is 5 volts, and then like ground is 0 volts. So all the wires in the computer at any time are either 0 volts or 5 volts. And that's what represents binary values. And also, so the like most basic part of a computer is a logic gate, which is it's made out of transistors, which are electrically controlled switches. And did the animation work?
You have to hit space bar, not the arrow keys.
Okay. Alright, so this is just what they look like, just so I'm not just talking about diagrams on the screen. This is actual things I'm talking about. Most chips have like a whole bunch of logic gates inside of them because it would be like pretty useless to have just one logic gate per chip. You can fit way more than one in there. And then, so this is how binary numbers are represented. You have, instead of, so in decimal numbers, it's 1, 10, 100, 1000, and each digit is multiplied by that place value, and then add those up to represent the number. In binary, it's 1, 2, 4, 8, 16, and so on, all the way up to 65,536, because you like work with those a lot when building computers. And then, all right, so because bits can be, binary numbers can be built out of bits, and logic gates do operations on bits, you can use logic gates to do math with binary numbers. So I have, and that's, all right, so I have, there's so this is an adder. There's 3 inputs. There's the 2 inputs from the number, should have made the animations faster, and then there's the carry input and carry output. Those will become important. So notice how the output is 1 because it's just adding 1 to a bunch of zeros for each of the inputs they're on. So does anyone want to guess what happens when both inputs are 1s? I know Daniel knows. All right, one of you can answer.
It just outputs into the carry out.
Yeah, because 1 plus 1 is 2, but 2 can't be represented in binary. It outputs, it's 10 in binary, which is a 2 in decimal. And then if I add 1 more, that's 3. So the place value there is 2 and then 1. So the total number is 3. And the second place value gets carried over. And then you can chain these together really easily. Oh, wow. Okay, so the carry inputs and outputs are connected together for all of them. And so notice how, like, there's still a carry input and output. This can be chained together to make even longer chains. And then, just an example of adding 2 bigger numbers together. So this is output 3. 2 to the third is 8. So that's 8 plus 2 to the 0. 1 times 1, so that the output there is 9, which is 4 plus 5. And then a better way to represent it with all the 2 input numbers grouped together. I should not have done that. And then, yeah, it looks cooler when it's looking better. that's like one basic piece of a computer that can be used to do that. It's also possible to do subtraction if you bitwise invert the second operand and then add 1, which you can do by setting the carry input to 1. And you subtract. I'm not sure how that works, but it does work. So everything I've covered so far is called combinational logic because the outputs are determined just by a combination of the inputs at any time. It doesn't have any memory or state. Now this is different, so the outputs are fed back in. Oh wait, I didn't explain what a NOR gate is. So the alright, so the output, this is an OR gate, so the output's high if either input is high, and then this is inverted. It's like the, that's what this circle means by convention. So it's stable right now, but now if the other input is set high, so the outputs are now in a different state, but the inputs are still the same as they were before. And this is how memory is built. Oh yeah, and also I have, so it is possible for when you first turn the circuit on, it will be in just a random state. Hang on, I can demonstrate this. So all the lights on there are like kind of randomly on or off. That's from all the, there's a couple thousand flip-flops in the memory used to control the display here. And when it turns on, they go to like one state or the other. It's hard to predict, like if they're manufactured slightly differently on the chip. I'm pretty sure that's why. Anyway. Alright. Next. Oh yeah, so that, just that by itself isn't all that useful. You can make a data latch by adding some extra gates before it. So this is, so the outputs of these gates are high only if both of the inputs are high, and NOT is an inverter, so it switches the input and output. So these 3 gates are, it's called a selector. This is like a really simple example. So if only one of these is ever on,
You tabbed out of the browser somehow.
okay, so only one of these is ever on at one time because of the NOT gate and the data input there. Now this is the edge triggering, which is a little bit confusing because if one of these is on and one of them's off at all times, and you think the output will never be able to be high or logic 1. But if you have, notice how this is on very briefly. I'll run the animation way slower. So this isn't entirely accurate because it animated the change in the gate correctly, but the simulation still had it. So this is made out of like transistors and electrical switches in the real world. So the output is gonna lag behind the input like very fast, but there's still amount of delay there. And for a very short amount of time, both of the inputs are high, and that enables the output to be high. And then this selector here selects one of these inputs to the flip-flop. I say what a flip-flop is?
Not exactly.
Anyway, that's what this thing is here. So now, there'll be next one. So now it very briefly, notice how I changed the data input too. So it'll swap the outputs here, right there. This means that if the clock is either just high or low, the data input can be whatever you want and it won't affect the output, and it'll like latch the data into the circuit. As long as it has power, it'll stay like that. And this is just a demonstration of how it works. Watch, this only updates whenever the clock goes from low to high. And so just one by itself isn't very useful, so there's a whole bunch of these. And also, alright, so this, I didn't explain this earlier. It is also possible because the way that logic gates output electrical signals, there's two transistors, one connected to power and one connected to ground. So two switches, and one of them's on, the other one's off at all times. There are also special gates called tri-state buffers. Keeps going. And then so you can set it so both the switches are off, which means the output can be in whatever state. And that's important. Something I'll explain later. And also this is the most common unit. It's the most common component I used in the computer. And then this is also how computer memory is built. So this has about the equivalent of 32,000 of those latches in one of those chips, and there are 4 of those right there and on the other side right there. And there's some more complicated logic to control which one is selected to be written to or read from at any time. And they're all of the outputs are connected together to one bus, so-called. That's why it's important for them to be able to turn their outputs off, because you don't want multiple gates connected the same way, because then it'll cause a short circuit when the outputs are set differently. Alright, so this gets more complicated. So if you change, this is how I did a lot of, this is how all the timing works in the computer. There are other ways to do this, but you can chain latches together. You need alright, so notice how the clock signals in these things are alternated. So one of them this one will update from that one, and then so on, and it loops back. You also need something to start it. That's why whenever I turn the computer on, there's a delay between when it receives power and when it actually starts doing things, because I have a big capacitor on that circuit board right there, and what that's meant to do is if any of these data latches, I didn't know about when I designed this, if any of these would just whenever I turned on, any of these would be set to 1. So I made sure to have, I didn't show it, but there's an enable signal for the whole computer, and it's initially off when it turns on. So if there are any ones, logic high values in these, it'll get flushed out. So the capacitor gives it enough clock cycles for them to be 0, and then it'll start the sequence. So there's those outputs and then it loops back. And then these can be chained together to produce more complicated signals to control things like reading and writing from memory and whatnot. I like to think of this, so this doesn't have to be so simple. This could go to some other sequencer somewhere else in the computer, based on what instruction is being run. It might be really complicated. And I like to think of the signal that's being passed around as a baton in a relay race, where only the person who has it is running, or so only one part of the computer at a time is doing something, and the rest of it is just waiting for the signal to start doing its thing. And then when it's done, it'll pass it off, in quotes, to the next part of the computer. And the board I was talking about earlier, that's the thing that originally starts the baton being passed around throughout the computer and starts it doing things. Alright, so now I'm going to talk more about my actual design instead of random diagrams. So this is another bus. So this is 8 wires, and it's along the bottom. horizontal board in the bottom of that, and it connects almost everything. And pretty much everything that writes to are 8-bit data latches. Most of the outputs are disabled so they don't conflict with each other. And then there's some other components. Most of these correspond one-to-one with like different circuit boards, but it's not exact. So this is just a thing that has like latches on it basically. So I can read data from whatever, like I can connect jumper wires to it. I ended up attaching the display to the outputs of that. It's pretty simple. This is like the memory. Oh, and I should say that most computer memory, like DDR4, 5, whatever, I don't know what it means, but it uses capacitors to store values, which is different and more complicated than just using flip-flops. So, yeah, I should. So, and that can also be written to and read from, like however the program wants. This is what's traditionally called the arithmetic and logic unit, and it's for doing math and logic. This one, the one I have, it's really simple. It can only do addition, like what I showed earlier, and subtraction, but you have to use more operations because it's pretty simple. And the rest of the operations are just bitwise, like it does an AND with the corresponding bits of 2 inputs and produces an output from that. This is the stack, which I'm not going to try and explain because I'm already being boring right now. So this is used for, how many people here have taken like a programming class, like in C's? All right. So you know how you have a function that has like, you define variables inside of the function, and then once the function is returned from, like there's no way to access those variables anymore. This is mostly this is what the stack memory is for, and you can only use it in very specific ways. It's like a stack of plates. You can put something on the top of it, which is called a push, and then pop something off the top of that. And I made it a bit more complicated so that you can reach down from the top and access data further down. And so that's used to store local variables and functions, and it's a lot more restricted than like the general purpose RAM, which would also be called the heap memory in like actual operating systems. And then this is the part that has, so the diagram I showed earlier with the baton signal being passed around, there has to be a clock connected to all the timing logic to make sure everything steps in the correct way and at the right speed. So this just has I originally had like a pretty janky resistor capacitor oscillator on it. If you have a capacitor and a resistor, it charges and discharges at like a fixed rate. Anyone in physics should know what that is. Right, Alden?
Physics is overrated.
Anyway, so
Physics was Tuesday.
So I ended up replacing that with some crystal oscillators, which are on a different part, but anyway. And then this is probably one of the most important parts. This is what tells the rest of the computer what to do. And it also has, it has the program memory attached to it. So every time it runs an instruction from the program, and I didn't mention how like a program is just a list of instructions, and they're run sequentially. And then this is the call stack, which is in like most programming languages, this is used the same. This is the like the same piece of memory as the stack, but I chose to make it separate to make function calls a lot faster. Now, I'm not going to explain exactly how, but I'll explain that one later. And then that's for addressing what reads to and writes from the bus. It's like the most, like how the computer like has, it can only do anything if like certain parts can talk to each other. So the most common instructions that I use in programming it are move and write instructions, and it's write is pretty much just a move, but from a constant stored in the instruction itself, not from somewhere in the computer. And this is what's responsible for, like, telling each thing, like, move a byte from the memory to one of the inputs in the ALU, and then running a constant from the program into the other operand, and then moving, like, the result of addition into the stack or whatever. That's what the bus is for. Then, okay, so this is the format for instructions. This is what I came up with like about a year ago. I spent a lot of time thinking about this and like how to put as much information in these as possible, but not making it too complicated. So the first 4 bits is always going to be like the type of operation it's running for. I believe there are 7. Yeah, there are 7 different ones. There's move, write, and a couple of other ones for flow control. Oh, and this is all the this is everything that can set the state, like write 1 byte to the bus, and this is everywhere that can receive a byte from the bus. And then write is pretty much the same thing. It's only different because all 8 bits here take up too much space. Why is it? Okay, so the animation doesn't work on this display, but it does work on my laptop, which is why this doesn't line up. But so 8 of these, this is 16 bits long. 4 of them always reserved for the operation code or opcode that tells it what to do. And then the destination. So if I had the source and destination, then I wouldn't be able to fit a whole like constant byte from the program. So that's why write is a different instruction than move. And then these are some other ones. So also a very important part that I should mention is if you just have like the computer go through each instruction one at a time until it finishes, it's not very useful because if you have a program, you'll know about like if statements where you can skip code or loops where you can go back and repeat code. And go to, that's an instruction for explicitly setting the program counter. It doesn't just go on to the next one. And then it's very similar to, this is the only instruction that allows the computer to make decisions, and I use it all the time when making like loops or if statements, any kind of flow control. So on that one, I don't actually have the hardware configured to work with that because there's some like complicated stuff and it wouldn't work. But I do have it in the design. And this is for function calls. It's pretty much the same as GoTo, but it stores the program address on the call stack first and then does a GoTo, and then return pops off the top of the call stack, and so goes to where the function was called from, so that it runs the function and then goes back to the original spot in the code that called it. Okay. Alright, so I was gonna make a whole bunch of animations, but I didn't have time to, so I have a Google Slides here somewhere. Alright.
Unrelatable.
I was gonna make like a whole like simulation of it working, showing all the states of the registers and whatnot, but that never ended up working, so. Alright, so I'm gonna talk about more of like how I actually designed it. So I already talked about the first 2, and then I had to figure out like the actual logic to implement things like addition and all the memory, stuff like that. And then this is an example. So I use this website called Circuitverse, which is a digital logic simulator, kind of like what the animations I was showing earlier, but it's way easier to use. It does have some things I don't like about it, like you can't select a whole bunch of stuff and then move it around. So if you have things placed awkwardly, that's like where it's gonna be unless you wanna manually change things, which is really annoying. And then this is the first thing that I designed, which ended up not working because I did dumb stuff with the timing. Actually, there's still a problem with it related to this that I haven't figured out, but I have been able to program around it. So this is the part that does all the math. It's like, it's the longest circuit board on there, it's that one. And it has addition, like what I showed earlier, and it has mostly just bitwise operations, bit shift, and also it has equality, which is really useful. And yeah, those are all the different operations for it. Alright, so this is the, also the, like the general purpose RAM, it's usually called the heap in like actual programming languages. And the stack memory is very similar. They both have the same, they're both 64 kilobytes, which isn't very much for today's standards, but it's enough for like anything that I would have that do. So I already explained what this stack is. And then, let's see. Oh yeah, I did have some, not animations, but I did explain. So this is like a program for the computer that doesn't really do anything useful. So, and this is the program counter pointing to one instruction at a time. So when it calls the function, it doesn't just go to the next line, it goes over to there, and then it puts a number on the call stack, which is the value of the program counter when it gets the function call. And then it'll keep going, and then it'll call another function from inside this function. This is why I can't use just a single register or variable in hardware, because if I called this function, it would overwrite the original return address, and then when it returned, it would return there correctly, and then when it did a return there, it would go back to there. So there needs to be memory that can hold a whole bunch of them. I believe the actual call stack on that has 256 levels. So if there's like a recursive function call that takes a long time to like resolve, it could overwrite the stack, and then it just runs instructions in here and then returns back to the function that called it, and then return back to the original program. Alright, does that make sense? I don't know how well I'm explaining this. Alright, next. So this is not like the other program memory, because I showed the flip-flops and also dynamic RAM with the capacitors that needs to be refreshed constantly. What's common to those memories is that they all lose data when it doesn't have power anymore. So when you start it up, it's just something random like the display. And the flash memory, I use these different chips, and they're all on that board right there. The way I program it is I have an Arduino that I hook up this thing, and then it loads data onto them from a program that I have on the Arduino. It's pretty janky, but it does work. And I can store 64,000 instructions in it, which is way overkill for anything that I've done already. But okay, so I had to do I make timing diagrams for everything. This was like the most confusing part. I spent like a lot of the time. This is over the summer when I was doing all of this, so I had a lot of free time, and this is what I did for a lot of it. And riding my bike. So this is also this website called WaveDrum, which I found. I don't know like who made it or anything, but it's pretty cool and pretty simple. You can write code into it, and it'll render the timing diagram for it in real time. And also, like last year when I was like thinking about like really basic stuff, how to build it, I thought it would be cool to have 2 different clock signals that look like that, And so the idea was to avoid race conditions where data changes at the same time as the clock changes. Like on the latch that I showed earlier, if the data input goes high at the same time as the clock, then it's not possible really to predict what the output would be. So if I have like one part of the computer running on just the B clock and the other part running on just the A clock, then, and they communicate with each other, then there's no chance that they would ever try to do something at the same time. I later realized that it wasn't really necessary because I could just like have a timing diagram for one part and then use that to design what comes after it, like what comes after it, like how the, in like the relay race that the baton is being passed in. And this is also what all the lights on this, it's not just for decoration, although it does look cool in the dark. That's for checking that the timing is working correctly. So when I was originally building this, I spent a lot of time there's a way to manually step the clock, and so I would step it forward and then check that the signals were either high or low by looking at the LEDs. I could see if there was anything wrong with it. Alright, so this is that part on the computer, not sure if you can see it. This is so for every instruction that's run, so this is 16 bits input, and this is also a screenshot from Circuit Burst. So you can like build all kinds of stuff, and it's pretty cool. And then it goes to this decoder, which I didn't talk about what this does. So like the baton, in air quotes, from the program memory that says that the instruction is ready, it goes into, I have it. So then this, depending on the opcode, so I was talking about move right, go to, call, return, halt, go to if. This decodes it into one of those. So move and write instructions are pretty much the same thing. Actually, they're run exactly the same on this piece of hardware. And then there's different go to, call, return, halt. So this is what runs each of the different types of instructions on there. And then these are like the types, these are the signals telling other parts of the computer. So it like sends the baton to another part of the computer depending on what it is. So it might, if it's a move or write instruction, it'll set this high, and then it will wait for the bus move sequence to stop, and then it'll come back on the left side there, and then it'll run the next instruction. Oh, and that's it in real life. I have the things on a paper there because I messed up the silk screen on the circuit board, so I had to label that correctly. Oh, and also, fun story, when I was originally putting this together, I had this whole thing connected like that. So there would be like a power input and a ground input on there somewhere, and they would have been attached backwards. I'm not sure how I managed to do that. I felt pretty stupid when I figured that out. Jerry, you can come in if you want. Anyway, he's wondering. So I put it on the correct way, and it did actually work. So I'm not sure why, but it's not easy to accidentally damage the logic chips on there. Alright, so that image is pretty dark. So this is like how I designed the actual circuit boards. I did a simple one so you can actually see it. So this is the startup controller. This is what like starts the baton when it powers on. And then I had to like replicate it in KiCad, which is a PCB, like electronic design program. It's pretty cool. And then you can design a circuit board, and it has auto routing, which is for this. I think I auto routed that. So all these connections on here have to, these are like the wires that connect things in the diagram. And it will tell you, like, if you click on one, it'll tell you where it has to be connected, but you have to like figure out where it goes. And for really complicated circuit boards, it's like not really possible to do. So there's someone built, some random person on the internet made a program to do that for you, which is really nice. And then this is the actual circuit board photo that I took like a few minutes before this started. I definitely wasn't rushing to make this. Alright, so then this is like beginning of the school year when I had designed the whole thing already and it was time to build it. This is also a pretty recent photo. So there's a lot of obviously all those are outlines for chips that have to be soldered on there, and that took a while. Yeah, that was, soldering is actually pretty fun. You just like melt it on there and it like glues on in the correct way, except when it doesn't. Oh yeah, so this was like most of what I did. I would put something together and then check that the timing would work, and it usually would. I messed up the outputs on like a chip layout in KiCad, so it generated the traces the wrong way, so I had to like take a pair of scissors and like scrape it off the circuit board and then wire some other things, solder some other stuff on there. Also, there's on the other side, you'll be able to see. Anyway, I also had to, this was what the LEDs were for. I had to check that they actually obeyed the timing diagrams correctly. Alright, so that's a picture of it partially completed. And at the time it was like just a couple of things like attached together and it was pretty flimsy. I also had like a ton of breadboards connected to everything. And then right near the end of the year, oh yeah, so I did get it completed like earlier than I thought I would. I was expecting this to take like all year to get working, but it's quieter now. So I had these like mechanical supports there. And then, yeah, I believe that's everything connected. So I had it working. I also had it running the stepper motor. It was fun just to like demonstrate, like just to like check that the ALU was working correctly. And then, so originally, as you can see, I didn't design like the rest of it with like this thing in mind because it's like a base and everything is made first, and then I designed and built that because earlier there's just like 16 inputs and 16 outputs, so I could just hook LEDs up to it. And I didn't like that, and I also wanted to play Tetris on it. So I designed the did I go? Oh, I did go forward. Alright, so this turned out to be really complicated because actually I can demonstrate it. Also, are there any questions so far? Alright.
That's fun.
Alright, so what does it is it doesn't actually power all the LEDs on there at once, because for that there's 32 by 32 of them, so you need 1024 outputs from a bunch of probably 8-bit latches, and then that would make the wiring on the board really complicated, and it would just be a pain to design. So what I have instead is each, trying to think of how to explain this better. So there's like 4 rows. Each of these chips on here has data loaded into it from memory, which is on this board, and you can see it's random pattern like what I explained earlier. And this is called multiplexing, by the way. So every time it shifts those 4 lines down, it has to load all the new data into the shift registers. These are very similar to like the sequencer I showed with the like the bit moving down the line and then back. These are similar to that, but each of the outputs is connected to a whole column of LEDs. Anyway, so the logic to like run this thing like a high speed. It did get really complicated, and I'm sure Dr. Hamlin remembers when there was the circuit board, that one there was a problem on it where I would attach the oscilloscope to like a digital output pin on one of the chips, and that would cause it to start working properly, and when you stopped touching it, it wouldn't work, which was really annoying because the scope is supposed to only measure something, not affect it as well. It'll also work if you just held a wire and touched it. So it turns out I don't have the circuit diagram, but there was a race condition where there was some really delicate timing going on where one thing had to happen before the other thing, and they were like really close. Like the timing was so close that it was affected by the capacitance of a digital signal. So if you slowed it down, it would work. And I did eventually fix it by attaching some capacitors between the signal and ground, which is not the best, but it did work. And didn't go into much detail about programming, but I was able to build a compiler for it. Not really a compiler, an assembler. Daniel built a compiler. Mine was way simpler than Daniel's. I just like had it like it's like 1-to-1. Each line is an instruction in the output. And I could also write programs for it and run them on my laptop. Like before this thing was even built, I could like write a program for it and test it, which was really nice. Also, so this is an example of a program. It's not like C++ or anything. It's in like my own version of assembly. We're all at Daniel's presentation, right? Anyway, so like each one of these corresponds to an instruction. I'm not gonna go into like actually how this works because I've been talking for a while, and I'll let this thing still. So you don't have any variables. You have to keep track of where in the computer, like the variable that you're using is. So like it might be somewhere on the stack. You have to keep track of where it is on the stack and stuff like that. It's pretty annoying to do, but also kind of fun because like the only data type you have is a byte. You can't have like floating point numbers or nothing fancy like that. Oh yeah, this is some specifications for it. It's not that impressive. I might build another one in the future that's better. I also don't know how high the clock speed can go because I'd be nervous to test it at like really high speeds because it could like cause like the baton that's being passed around to be duplicated if the timing between something doesn't work, and that could actually cause hardware damage. I think, I have no idea. So what I learned like a lot of things from this project. First of all, this is another example of the real world not working the same way as in the simulation, because I did build the display in the simulation and it did work fine, but it didn't work in real life. This is because this was on actually this was the first board that I soldered together. There was so when the logic chips, like one switch turns on, the other turns off when it switches states. Like, Dr. Hamlin, is this right? Correct me if I'm wrong, but like very briefly it will draw a lot of current because they're both partially on, and that causes currents in the circuit board traces that supply power to the chip, and then that can creates magnetic fields and complicated stuff, and that causes other signals to be messed with. So that's what's causing that to happen on the scope there. And I also learned about how hard it is to actually damage chips because I had that hooked up backwards. I definitely want to do more of this. I'm doing electrical engineering, WPI, this fall because I think it's really cool. Work with electricity and make it do things. Also, programming and assembly is like really weird. It's not like any other programming language because you're like telling the computer like actually what to do for each cycle. You have to think about stuff. Like if you set the carry input, because there's a way to set the input bit on the adder in the ALU. If you set that somewhere in the program and then somewhere else you go to add two numbers together, the result might be off by one because it's still set that way. You forgot about it. So stuff like that you have to watch out for. I'd like to thank Dr. Hamlin for letting me use the makerspace like for a whole year, and also all those resistors. Actually, you know, I did actually get some of my own resistors, but I did use some. Also for Dr. AG for letting me do this presentation, even though it wasn't an actual independent study. Also for my parents for like helping me like pay for this because it was kind of expensive to build. And also I have this random book at my house that I've had for like a really long time, like since I was little. And that's taught me like pretty much everything I needed to know to build this was from that book. A little bit more was from another book Dr. Hamlin gave me last year about computer architecture. Thanks for showing up. And are there any questions? Yeah.
Can you play Tetris on it?
Yeah, that's the whole point of trivia. I did not know I was going to be talking for like 50 minutes. Let's see.
Watch it completely break.
Yeah, this is going to be the part where it doesn't work. Also, it looks better when the lights are off. If you want to come look at it up close, you can see all the like the timing lights on there flashing really fast. It's running at a lower clock speed. Let me press that to start it. All right. Oh, I added
play right here.
Yeah, this is Peak Gaming right here. I added a drop button because it was originally going too slow when I was testing it. So it does, I can shift it. This is like the most optimized I could make it. It was originally about 7 times slower than this. I messed with the program a bit and made it faster. Also, you can leave now if you want. This is like, what's
Why do you have the stack and program and heaps separate? Is
Because-
the stack's fast or something?
It's just like simpler to so okay, so the way that I have realized that I made it a little bit complicated where the stack is like the stack pointer and all that, and like pushing and popping, it's all controlled by hardware. So I can't just it was easier to think about having them separate. I'm not sure why I did that. I think Dylan?
So did you, I assume you wrote Tetris in assembly. How was that?
Maybe like a couple of weeks, and like the program's like, I think it's like 1,700. It's 1,700 instructions. So that would be about the number of lines. And also, never mind. Also the way I program it is I have the assembler. I have a Rust program that puts it onto what?
The anti-rust crowd back here.
It's pretty cool. Anyway, so I have to like copy and paste the program into some Arduino code. And then I plug the Arduino into some pins on the program memory. I also have to make sure that a wire here is disconnected, unless otherwise it'll power the whole thing when I turn the Arduino on. And then, because Tetris was so big, it wouldn't fit in the Arduino's memory because it's so stupid and like it only has like 2 kilobytes or something. No, Daniel ran into that problem, or Jake, anyway. So I have to like load it in chunks onto there, but it does work. And I'm too lazy to figure out how to like actually clock it in over serial. So should be able to complete all right now. All right. Any other questions? Yeah.
What controls do you have on your computer? Like, 'cause I see you have a little control panel there, but like, what kind of buttons do you have on that?
Also, you all can like come look at it closer if you want. So I have